Hello again to the course Relativity and Cosmology. We started with Special Relativity, our chapter 3, and after the introduction and the presentation of the relativity principle, I went into more details discussing the Lorentz transformation here. I put them again down for a 1 + 1 dimensional example, including the speed of light, which we'll later set equal to 1. And today I want to go on and discuss important consequences that we can already see in the 1 + 1 dimensional diagrams. And these are the famous effects time dilation and Lawrence contraction. I mean, a metaphor says running clocks go slower and moving rods are contracted. Now, we had seen that in the Lorentz, or even more general, the Poincare transformation, we have this invariant. So c squared t prime squared minus x prime squared, where the primes refer to an inertial system I prime. It's the same as c squared t squared minus x squared, which refers to an inertial system I. And we can write down the infinitesimal version of this in the following way. So ds squared, which is defined actually by this right hand side as minus c squared dt squared plus dx squared. So that's an important quantity, and this invariant, this infinitesimal invariant, we call also the line element, because it gives an infinitesimal distance between events in space-time. Now this here in 3 dimensions, I mean this was only for one spatial dimension, is a shorthand for dx squared plus dy squared plus dz squared, which is the infinitesimal Pythagorean line element. Maybe at least once I should emphasize that this is the common notation, but what it means is actually that you square the ds and that you square the dt, and also you square these. But it's common not to write these parentheses. No? So it's not a d of the s squared, it's a ds squared. Now, quite generally, the Poincare transformations we can characterize as being those transformations that leave the ds squared invariant. Let me again draw a picture. So an inertial system I, t, and x, and because of this invariant, this means light always propagates along the same straight lines with inclination 45 degrees to the axis, and so we have local light cones that look like that, and they look locally all the same, so they are not tilted, also they are absolute. This will no longer be the case for the general relativity, because there we will see that space-time is curved and that this will also affect the light cones. But here in special relativity they are rigid, and if you are a world line, time-like world line, then you can move here, not necessarily inertially, but you can move here, but always such that your tangent vector is inside the light cone. So it could, for example, look like this here. No? So that would be a world line. And if you go to an instantaneous rest frame, then the time axis would be tangent to the world line. So here, if you have here the tangent here, so that would correspond to the instantaneous rest frame where this moving body is at rest, and you can associate with it a momentaneous inertial system, which is that rest frame here, and that you assign here this t prime axis and here this x prime. And so if the green line were inertial, then of course it would be always the same inertial system, the rest frame, but here it's accelerated, so you can have a different instantaneous rest frame at all time, and this differs from point to point in generally. Now the rest frame is of course defined by being at rest, and this means the x prime is equal to 0. So this is the instantaneous rest frame I prime, and the rest frame is here characterized by dx prime is equal to 0. So you carry these coordinates with you, and only time elapses for you because you stay at the same values of your coordinate system. And so from this here you have then that ds squared, the invariant is minus c squared dt squared. So we can introduce a proper time, tau, by the following. So ds squared has the dimension of a length squared, but we can define the proper time. So in German it's Eigenzeit, that's what Einstein also used, tau. Infinitesimally by d tau squared is defined as minus ds squared over c squared. So this proper time is an invariant quantity, and actually it's used for the definition of time since 1967. We use atomic clocks, and special relativity is implemented in the metrology of these atomic clocks, because how these clocks, they move in generally, of course, but they all have this invariant proper time, and this is actually what these clocks then show. So these are these measures time intervals shown on a co-moving clock. We have here this minus c squared dt squared plus dx vector squared. So you can compare this with, as I already mentioned, the Pythagorean line element. So compare this with, let me call it d sigma squared, which is dx squared plus dy squared plus dz squared. Okay, here I call it the x vector squared, but more precisely, so this is the line element of Euclidean geometry. So this is the line element of Euclidean geometry, the infinitesimal version of Pythagoras' theorem. But so here, if you compare this here, so the three-dimensional part is the three-dimensional line element, but here you have also the temporal part, and you see the temporal part very essentially has here a minus sign. I mean, this is what really is the center of all of this, because otherwise you would not have a space-time. You would just have a four-dimensional space, which would not give you any dynamics. And because of this minus sign here, when you draw a diagram, then a world line that looks longer in a, say, on the blackboard, in fact has less proper time. And this is because of this minus sign. You know that, for this here, the straight lines, they minimize the distance, and the curved lines, they are bigger, but here it's just the opposite. Straight lines still extremize the length, but they maximize it. So, for example, if you have the following world line, so t and x, and a world line 1 that is at rest here in that inertial system, so let's call it 1, and another one that's where you have an acceleration. You go here to some far away distance and or near distance, and you come back. So this is a world line 2. And so as it looks like, because the blackboard is of course a Euclidean geometry, this is it's longer. No? It is longer in that geometry, but we have to use this line element here with the minus, and then of course for the proper time, which is here with the minus, then you have to subtract this minus dx squared, which means that this here is in fact smaller. It has smaller length from the space-time point of view, even if it looks like that. Moreover, the extreme case is the light propagation. So if you have here a light propagation, so this has even zero length, no? Because light propagation means that ct is x, so the ds squared is equal to 0 exactly and always for the light propagation. So this here has zero lengths, although it appears, of course, on the blackboard as having some lengths. So this is extremely important. This has zero lengths. We will discuss this further later. Also, we will discuss this in the beginning of chapter 4 on the twin paradox. So this is the essential difference here, and so what I just said refers to the d tau squared, which is the infinitesimal proper time. Of course, if you go to the more frequently used ds squared, then it's a negative of that. So this means that this here certainly is more negative and this here is less negative. But it's more intuitive to think about the d tau squared here. Now let us set again speed of light equal to 1 to emphasize the geometric structure, and we go again, like here, to one space dimension. And this one space dimension is the x dimension. So again, c equal 1 and one space dimension. For simplicity, we describe a world line in an inertial system I by x of t. So x of t is a world line in I. An arbitrary one can be accelerated. And let us, from the point of view of I, write down the line element ds squared, which is minus dt squared plus dx squared, so one dimension. And now, if we evaluate this along the world line, where we have x of t, then we can write here dx of t, and this gives us the following: dt squared minus 1 plus dx of t over dt squared. No, so that's just here inserted x of t, but I did this because dx of t over dt, as you know from Newtonian theory, is just the speed or the velocity more generally. So this here we call v squared, the speed squared. So we can write this as dt squared minus 1 plus v squared of t. Now if you go to the proper time, then we have d tau squared is minus ds squared, and this is dt squared times 1 minus v squared. And which means that if we write this down for the d tau themselves, so we can have from here that d tau is dt times square root 1 minus v squared, which you see is smaller than the dt, or you can also have the reverse. So the dt is 1 over this times the d tau, but 1 over this is just our gamma factor, which we had introduced earlier. So this is gamma d tau. Now what do you learn from these expressions? Well, you learn the following. You see that here the d tau is smaller than the dt. So this here, d tau, is what is shown by the co-moving clock, and it shows that the interval on the relatively moving clock here is smaller than the interval that you measure in your inertial system. And this is what is meant when people speak about moving clocks are slowed down, which is a metaphor because it does not here refer to particular clocks. It's a property, as you see, about space-time. And you will immediately understand in a minute when I draw the diagrams that this is really an effect of space-time. And this is why it's called time dilation. Time is, so to speak, metaphorically slowed down. Now you see here that there is this factor gamma, or 1 over gamma, between the tau, which is the running of the moving clock, and the t, what you read of a clock in your inertial system. Now, when you have a generally moving clock, then you integrate the proper time along the world line to have the total world line. So you have your inertial system from which we make the observation. So here, and we have here, say, a TA, time TA, and a time TB, And we have here, so that part of the wavelength of the line element between the two times A and B points. So what is the proper time between A and B? Well, we just have to integrate the infinitesimal proper time d tau from A to B. So the proper time from A to B is tau AB is the integral from A to B d tau, which is the integral from TA to TB dt. This is what we had here. dt times the square root 1 minus v squared of t. So the v of t can be anything. And so this your cesium clock, for example, your atomic clock moves around, and you can read off that clock, and it shows the time here that you get here from this integral. Now let me go again to a space-time diagram, and let me explain to you the reciprocal nature of time dilation. So let us go to a diagram Tx, which of course is addressed in inertial system I. So here again is the light propagation, and so let us consider a moving inertial system T prime and x prime. No, you remember that in special relativity we also have to move this x-axis. Now recall also from what we had earlier that the unit points on all axes, they lie on a hyperbola, they are on hyperbola. So if this is the point 1, then we can have here the point 1 here, and this hyperbola asymptotes the light propagation. So we want now to see how an observer in I would see the time running of a clock in I prime and vice versa. So you see here that if I'm here in I, then of course to get the time I have to make the parallel to the x-axis. So let me draw this in blue. So here this event, which is time 1 for I prime, would correspond to that time here in I. And you see here this is bigger than 1. So what observer I prime would call 1, say 1 o'clock or whatever, for here is for the observer who is at rest in 1 is bigger than 1. And now what is time 1 in the inertial system I, what would that correspond to in I prime? Well, we have to draw the parallel to this x prime axis, so we would have to have roughly this here. So you see here this would correspond also to a time bigger than 1 in I prime. So you see the two observers, I and I prime, they don't agree on what they read off their clocks. I mean, the clocks are identically manufactured and so on. So the observer here would say that time 1 here corresponds to a bigger time here. So for that observer, the moving clock is slowed down because it's only 1 o'clock, and here it's already more than 1 o'clock. But the same also for I prime. Not that looking at the clock of observer I would see, it's only 1, while my own clock is bigger than 1. So you see, this is not something mysterious about properties of clocks, which is hard to understand, but it's an effect of the space-time structure. And actually it's an effect of a consequence of this light cone structure that we have here and the corresponding non-validity of absolute simultaneity. So you see time dilation is a reciprocal effect. So there's no paradox with that, that mutual observer say, well, the other clock is the slower one. It depends on how you measure time. No, and time by itself is not absolute, and space is not absolute, only the light cone structure. And this is why they do not agree, although it's the same space-time structure. This is very important. This is why I spent some time here. Now, if you have an effect for the time, and you know already that space and time are connected, then of course we should have a simultaneous effect for the space. And in fact, this is what is the case. And the analog to time dilation in space, this is in effect called Lawrence Contraction. So the analog to time dilation in space is Lawrence Contraction. They're named after the Dutch physicist Lorentz, who before Einstein had used this formula in a different context, not in the context that Einstein had here. Now, it refers to the measurement of the length of a rod, or of a certain one-dimensional object. Now, how do you measure that? Because if I have a one-dimensional object, say this piece of chalk, then okay, naturally you know how to measure this. You have this as the front end, and this maybe as the rear end, and you have a scale, and you say this is so and so many centimeters. But what is implicitly behind is that, of course, you measure here this and the scale of this and this at the same time. Yeah? So I mean, you refer to this at a given time, because if this is moving, so you measure this here, then you let it move, and then you measure here, of course you get a bigger one. So this is not what you do. And this is maybe trivial in a classic context, but here it's important. And so we can formalize it in the following way, that we say the size of an object is the cross-section of the world tube of that object in space-time at t equals constant. So we call the size of an object is the cross-section through the world tube at t equals constant. And you see already here, when I write a t equal constant, it has to do with simultaneity. And simultaneity is no longer absolute. And this is why you have this effect. Let us go to the diagram. Now, I should perhaps write down, this is the spatial distance of simultaneous events. So if we have again this diagram here, so we have here t and x, and we have here the light propagation, and we again have this hyperbola, say, here, so that we have here, say, 1. Now we consider a rod that is at rest in a moving frame I prime. So if I have here, say, a moving frame, so t prime again, and here x prime, and this would correspond here, that here, this here is, say, the length of that moving rod as measured in the rest frame. And I call it delta x prime. So maybe this should also write down the 1 here. So this body, this rod, moves with respect to our inertial system I. So what is the size of that rod in our system? Now, of course, you would have to compare the two. We have the two world lines. So this is the rear end, and then of course you have here this point is of course in space-time also a world line, so which looks perhaps like that. So here, so that's the rod in the world tube of that object. So if I measure the length of this in the system I, then of course I have to use my x-axis. I have to use t equals constant, and I have to use this distance here, which is which I call delta x. And so you see here, this distance here, delta x, is smaller than 1. So I would say that this moving rod actually has not a distance 1, say 1 meter, but something less than 1 meter, maybe 90 centimeter. So I would say that that rod that moves, say, away from me is contracted. And this is what we call the Lawrence contraction. But again, this is a reciprocal effect, because if you view this from, or if you have a rod delta x in I, then of course you would have here this world line, and you would see that it would correspond also to something smaller than 1. Well, sure, sorry, I mean, if I had something 1 here, then you would also have something smaller than 1 in the red system. So this is again a reciprocal effect. So we have all identical rods, or say of 1 meter. They move with respect to each other, and we cannot say who is at rest, of course, it's relative. But if we observe from our system the moving one, we conclude it's contracted, and the other one would conclude the same. And it's not that this is a real effect. I mean, they are not. It's not that the material experiences some stress or whatever. It does not. It's just that the definition of simultaneously, of course, depends on the system. So rod at rest in I prime is delta x prime, which is 1 in the diagram, and I measures delta x smaller than delta x prime. So the rod appears contracted, but this, as just explained, is a reciprocal effect. Mathematically, we would expect something similar here to the time dilation, and in fact this is what turns out. So if we have x prime is gamma times x minus vt, and we set t equals 0, which is this here, then this is gamma times x. So we get from here that the delta x is gamma to the minus 1 times the delta x prime, and which is square root of 1 minus v squared times delta x prime. And you have here the same formula or similar one as for the time dilation. So this apparent contraction appears with the same factor gamma, or 1 over gamma. You could also say, yeah, this is because from the point of view of I prime, I does not measure the two ends of the red at simultaneously. Right? So this is as if I measure this here and this one a bit later, and then it's of course shorter, and vice versa. So all of this has the same origin, and all the other effects of special relativity too, they have the same origin, because time is no longer absolute, and space and time become non-trivially mixed when going from one inertial system to another. So far for these two effects that one can nicely explain at a blackboard. So next time we have to liberate us from this 1 plus 1 dimensional situation and from the pictures. So we have to devise a formalism that is able to give us a machinery in 4 dimensions without relying, say, on pictures. And this is by the formalism of 4 vectors. So thank you for your attention today, and let's meet then for the 4 vectors next time.